Hi, George Romanic here. Welcome to Fundamentals of Weather and Climate. When we have very low temperatures outside, then wind tends to increase discomfort of human body. And it can also sometimes cause frostbites. Frostbite is freezing of human tissue. In the worst case scenario, wind in combination with low temperature can also cause hypothermia, which is drop of the temperature of human vital organs below 35 degrees Celsius. And that can either cause severe damage to those organs or, in the worst case scenario, death. All this is because wind is very good at removing heat from our skin. And that is why in winter many meteorological reports contain the so-called wind chill equivalent temperature, or simply wind chill. Let us examine how wind contributes to removing heat from our body. Consider a part of the skin that is exposed to the atmosphere, like skin on your hand. We can represent it like this. And now below is deeper layers of the skin and tissue. Above is the air. Between skin and the rest of the atmosphere, there is very, very thin layer of air that is called boundary layer. And this boundary layer has thickness of only about 1 millimeter or so. Very, very thin. Above boundary layer is the rest of the atmosphere, and we call that ambient atmosphere. So what is the importance of boundary layer and how is that related to wind chill? We will first examine condition when there is no wind. Wind equals 0. In that case, what is happening here is that our body, our skin, is warming this air in the boundary layer through the process of conduction. Now, from my video on conduction, we discussed in great details that air is very inefficient at conducting heat, which means the heat from boundary layer is inefficiently conducted to the ambient atmosphere through this process of conduction. So the skin warms up boundary layer, but then boundary layer is very poor at warming up ambient atmosphere, which means heat stays trapped in this boundary layer. And therefore boundary layer serves as an insulator for heat loss between our skin and the rest of the atmosphere, namely ambient atmosphere. That is one purpose of boundary layer. Another purpose of boundary layer is to have similar role, but when it comes to rate of evaporation. Namely, our body also evaporates liquid water, and then we have water vapor here in boundary layer. And concentration of water vapor here is much higher than the concentration of water vapor in the ambient atmosphere. But once again, air is very poor at diffusing water vapor from boundary layer to the ambient atmosphere, so it happens very slowly, and therefore most of the water vapor stays here, thereby decreasing rate of evaporative cooling. That is therefore the second role of boundary layer. And in both of these roles, boundary layer serves as an insulator between our skin and very cold ambient atmosphere. However, what is happening now if we do have wind? So wind is not 0, and wind starts blowing here across the ambient atmosphere and also across the boundary layer. Well, wind is very efficient at removing heat and this water vapor from the boundary layer. So this warm air here is moved by the action of wind, as well as this air here. So there is no more boundary layer of the order of thickness few millimeters to protect us and serve as the buffer zone between the skin and the ambient atmosphere. What is really happening though is that the boundary layer becomes very, very thin. Boundary layer can never disappear and go literally to zero, but it can go to so small value, much below 1 millimeter, that the heat loss between our skin and the air is very high, because this buffer zone, this boundary layer is very thin. And it is very thin because wind tends to remove all this sensible heat that we lose, as well as all water vapor that we evaporate, thereby improving the rate of sensible heat loss and latent heat loss. You might say, what is the necessary wind speed to cause the depletion of this boundary layer? Research showed that wind speeds of around 0.2 meters per second, very low wind speeds, already start thinning that boundary layer. This is very important because the average speed of human walk is between 1 and 2 meters per second. 1.4, 1.5 meters per second on average. So that means even if there is no wind and you are walking down the street, relative to you there is wind of 1 to 2 meters per second. And that is already enough to start reducing the thickness of boundary layer and therefore promote heat loss through sensible heat loss and latent heat loss. This boundary layer is thinnest when the wind speeds are around 15 meters per second, 15.5, 15 meters per second. To get proper physical understanding of the value of wind chill, let's consider an example where the air temperature is 5 degrees Celsius, so above freezing. And let's say there is no wind, wind off. Here is our skin that is sitting at much higher temperature than the ambient temperature, let's say 37 degrees Celsius. Although that's the temperature of our inner core, it doesn't necessarily need to be temperature of our skin, but for the sake of argument, let's say it. And what we discussed earlier is that your body is losing heat through conduction and evaporation. But that heat stays in this boundary layer for most. Now let us turn the wind on. Wind is on, and meteorological reports, depending on the value of wind speed, might say, let's say, that wind chill temperature, let's say Tc, is equal negative 5 degrees Celsius. What does that mean? This is now the key. What does this mean with respect to this temperature and with respect to this process over here? Very important what I'm about to say. This value over here means, yes, outside temperature is 5 degrees Celsius, but because there is wind, you will start losing heat at a rate as if outside temperature was negative 5 degrees Celsius and there was no wind. One more time. Wind chill of negative 5 degrees Celsius in this case means that the rate of heat loss from your skin will be equivalent as if the air temperature was not 5 degrees, but rather negative 5 degrees Celsius and there was no wind. Or in other words, we could reverse. We could say ambient temperature is 5 degrees Celsius, but there is wind. So from the point of view of the heat loss, it will be equivalent as if the ambient temperature was negative 5 degrees Celsius and there was no wind. That is the physical meaning of wind chill. That was first important point. Second important point is the following. In this particular scenario, keep in mind that your skin temperature or body temperature can never drop below 5 degrees Celsius. Body temperature or skin temperature can only drop to the value of ambient temperature. But it matters a lot how we get there. With this value of wind chill, we are going to get there much, much faster than if there was no wind and our body perceived the actual air temperature of 5 degrees Celsius. So if this was heat loss when the air temperature is 5 degrees and there is no wind, then heat loss with this wind chill would be substantially higher. We would lose heat at much faster rate than without wind or without wind chill. So what happens is that if your body cannot replenish this heat loss, the skin temperature will start dropping. In this particular case, it can only drop to 5 degrees Celsius. Of course, let's assume that if this was negative 5 to begin with, and with this wind chill, maybe this would be now negative 20, let's say. Now the situation is even worse. Because the outside temperature is below freezing, which means your tissue can actually freeze, but it will freeze, or rather, your body will lose temperature and get to this freezing point at a rate as if the outside temperature was negative 20 and there was no wind. In other words, this heat loss through both conduction and evaporative cooling would be extremely substantial. Now let us see the actual quantitative relationship between wind speed and ambient temperature, because people calculated for given outside temperature and given wind speed what would be resulting wind chill. Here is a table that shows actual air temperature in degrees Celsius, and the first column is wind speed in kilometers per hour or meters per second, whatever is easier for you. And then the rest of the table are the values of wind chill. So we can see if the wind speed is, let's say, 30 kilometers per hour, which is around 8 meters per second, and the temperature is negative 10 degrees Celsius, that the wind chill will be negative 20 degrees Celsius. It is much easier, though, to analyze this table in the following way. It's the same table, but there are these different colors that indicate different levels of risk of skin exposure to the outside ambient air. You can see that for the low values of wind chill, there is low to moderate risk of frostbites. But as the wind chill is increasing, and that means wind speeds are picking up and temperatures are dropping, then this lower right diagonal part of the table becomes very severe. Already here we can see that we have very high risk of frostbites in only 5 to 10 minutes. And then severe risk where you can get frostbites in only 2 to 5 minutes. And then when we go to the purple zone, it is extraordinarily low temperatures, and it's the best not to be outside and risk any frostbites whatsoever. Take a snapshot of this table if you need it for some research project in your school, and I suggest you study this more because it's a very interesting topic that directly relates human body and weather. With that, I would also like to mention a few deficiencies of this wind chill concept. First is that the wind chill was developed in the whole theory started being considered in 1941 when researchers in Antarctica studied how water in plastic tanks freezes under different wind conditions. And Antarctica is perfect place for that study because A, it is very cold, the coldest temperatures on this planet, as we studied in one of the previous videos. And also it's very windy place. There are the so-called katabatic winds blowing in Antarctica, which I will discuss later in this playlist. So it's very windy, very cold, so it's a perfect place to study wind chill. The issue is, over there people studied how water freezes in plastic tanks, and our body is significantly different. So that's one deficiency. Another deficiency is that wind chill does not account for the absorption of heat of our skin, our body, through short-wave radiation from the sun. Namely, even if it is very, very cold, but there is a little bit of sun, we get a lot of heat from the sun. Third, this does not account for significant spatial and temporal variations in wind speed. Wind speed is one of the most variable parameters in atmospheric sciences. So depending where you are, in a city, around a building and so on, the wind speeds can be significantly different to what was reported in the meteorological report. Particularly keeping in mind that wind speed at weather stations is measured at 10 meters above ground, and that's much higher than the average height of people. The so-called pedestrian height, average height of people, is 1.75 meters. And 1.75 meters is significantly lower to 10 meters where wind speed is measured and used for these analyses. Next, it's also important to say that the wind chill depends on body type. The thicker bodies lose heat at a slower pace because they have more heat-producing cells to replenish heat loss. It also depends on what part of the body is exposed to the outside ambient temperature. If it is parts like ears, that's very bad, because you see, ear is very thin. That means there is very little heat-producing cells, but it has very large surface area, so the heat loss is very large. That's why your ears always are the first one to feel cold if you don't have hat. Similarly, fingers. Fingers have very large surface area, but they are very thin. That means very small number of cells that produce heat, but very large surface area to lose that heat, and so on. And lastly, this index also doesn't account for the activity that you are maybe carrying out outside, if you are running, jogging, standing, and so on. And it also does not account for the subjective feeling of people losing heat and temperature. Some people are just taking it better, so to speak, than some other people. I'm one of those that is not very good at low temperatures. I like warm weather, sunshine, and beaches. But some people enjoy very cold weather. Until next video, goodbye.